So we're going to start with a question. As you can see, I hope you can see my screen. You're all welcome to the seminar. We'll start with a few questions in pure math, and then we'll go to a few questions in. We'll move to a few questions in applied math as well. This is the first question we'll look at. Falls under calculus, which is differentiation. And we've been told that a landowner is preparing to use a wire mesh to fence a rectangular piece of land that has that area with one side of the land existing along a straight wall. Due to the existing wall, fencing is required on the other three sides only, and a space for a 12-meter wide gate. I hope that zoom is better. So, due to existing wall, fencing is required on the other three sides only, and that's what we have there. We're told that the land is being fenced at that rate, the LDC, which is 12 minus 0.12 meters per hour, for T being from 0 to 12. If it's not clear, please pinch your screen so you can zoom in more. The land is mostly flat but has a depression to be filled with 200 meters deep topsoil. The land also has a small anti-hill in the center whose shape is modeled by the equation 12 minus 3x squared, where x is the horizontal distance in meters of the anthill and y is the height of the anthill in meters above the flat hill. The anthill must be removed to ensure that the land is fully leveled. The soil will be used to fill the depression. However, the landowner is not sure whether that soil will fill the depression. The landowner needs to determine the most efficient way to fence the land. So the first thing we've been asked is to calculate the minimum length of wire mesh the landowner must buy to completely fence the land. So we can have a sketch of what's going on. That could be our wall, and if we draw this, we have to leave space for the gate because we are told that the side with the gate is opposite the existing wall. And so we know that the area of this rectangle here, even with that hole for the gate, the area of this rectangle is 39,200 square meters. And if we decide to call the length of this side x and the length of this side y, we know that right here there are 12 meters left, 12 meters left for the gate. And so if the length of wire mesh that we're going to use to fence this land is L, then we can say that L is equal to 2x plus y minus 12. One x for the upper side, another x for the lower side, and then for this side with the gate, y minus 12. But we also know that the area is xy, because area is the length by the width. Area is the space being occupied inside. So the area is xy, and that means xy is equal to 39,200. And so we can write y as 39,200 divided by x. And once we have this, we can start to see that in our expression for L, that this becomes 2x plus 39,200 divided by x minus 12. Now, because we want to get the maximum of L, we have to get the derivative of L with respect to x. So we'll get the L dx, which is 2 plus 39,200 is going to be a negative actually, divided by x squared. You have to be thorough with your differentiation because you know that 39,200 divided by x is the same as 39,200 times x to the power negative 1. And so if you use the rule of, the power comes down as a multiplier and then reduces by 1, you have negative 39,200 times x to the power negative 2, which is exactly this. So we know for minimum L, the L dx has to be, 0. And so if the L dx is 0, then we have that expression is 0. 2 minus 39,200 out of x squared has to be equal to, 0. Now when you solve this, you end up getting x squared as 39,200 divided by 2, which is 19,600. And so this means that your x would be plus or minus 140. But now we can't have a length, we can't have a length being, negative. Okay? And because we can't have a length being negative, uh, we can say that x cannot be negative. X cannot be negative, and therefore x has to be 140. It'll also be good practice for you to check if this actually gives you a minimum. Now you can use the second derivative test just to confirm this. We use the second derivative test. We'll have the second derivative of L with respect to x will be, now you're differentiating, you're differentiating, write this on the side, you're differentiating negative 39,200 times x to the power negative 2. So what do you get? You end up with 78,400 times x to the power negative 3, which is divided by x to the power 3. Now, of course, if x is positive, this is going to be greater than 0. It is greater than 0 if x is greater than 0. And therefore, it will give us a minimum. If x is negative, it will be less than 0. And therefore, the expression will give us a maximum. So actually, x is equal to negative 140 gives you a maximum, and x is equal to positive 140 gives you a minimum. Now the question, what was the task? The task was calculate the minimum length of wire mesh the landowner must buy it completely fence the land. And so, if we found our x, we can get our y. Y is, if we just go up a bit, y is 39,200 over x. This is going to be 39,200 out of 140, which is 280. And so L, the minimum length required to fence the land, which will be minimum L, will be, with the expression for L, it's 2x plus y minus 12, yeah? 2x plus y minus 12. That's going to be 140 times 2 plus 280 minus 12, which is 548, 548 meters. That should be the answer for the first part. Now the second part is about the number of days required to install the wire mesh. Now, if you look at that bit of, I think the third paragraph, it tells us that the LDT is 12 minus 0.1 meters, in where the LDT is in meters per hour. T is the time in hours and L is the length fenced in a day, but also given a specific range for T. So T cannot go beyond 12. So if we integrate and find L, even with the respective limits, we'll be able to get the length fenced in a day. We have that dL dt is equal to 12 minus 0.1 T. We'll just take the dt to the right. We'll have dL is equal to 12 minus 0.1 T dt. And then from here, we'll integrate both sides. And on the right-hand side, we can actually include the limits of T. 0 to 12, 12 minus 0.1 T with respect to T. Now, if you know how to integrate, you know that here now, when we're looking at these algebraic functions or polynomial functions, when you're differentiating, the power becomes a multiplier and you reduce the power by 1. When you're integrating, you increase the power of t. Here we're integrating with respect to t. You increase the power of t by 1 and divide by the new power. So it's the reverse process for differentiation. So here we'll have 12t, and you can see when you differentiate 12t, you get back 12. And here we'll have 0.05 t squared. And you can see when you actually differentiate this, you get back the 0.1 t. And we'll be computing this from 0 to 12. This means you substitute the upper limits where the t is related to the 12, and then you subtract the value that you get when you're substituting the lower limit. Now, because the lower limit is 0, we don't have to worry about substituting it. So this will just be 12 times 12 minus 0.05 times 12, 12 squared. And this is going to give us 136.8. What does this mean? It means that, sorry, on this side we have L. So it means that the length fenced in a day is 136.8 meters. This is the length fenced in a day. And so, if that's the length fenced in a day, and we have to length a total of 548 meters, how many days is it going to take us? So we're going to have to get this L divided by this L. It's going to be 548 divided by 136.8. So that's meters divided by meters being fenced in a day. And the answer is, if the exact value of the improper fraction is reduced form is 685 divided by 171. You write this as a mixed number. This is 4, 1 out of 171 days. Now, of course, if we're talking about a whole number of days, this has to be 5 days, because in 4 days it won't be complete. So the number of days required will be 5 days, because in 4 days it won't be complete. So it's not a matter of approximation, it's a matter of what's the minimum. Okay, how many days do we need to go? How many days the number of days required to complete the work is 5 days. It's 5. Yeah, so that would be the answer to that particular part. And now for the next part, we're going to sketch the cross section of the anthill. If you look at the part where the anthill is, we have that y is equal to 12 minus 3 squared. Gives us the sort of cross section of the anthill. So basically, what we're being asked to do is sketch this curve. But more than that, we're going to sketch this curve just above the x-axis. We're not going to worry about the portion of this curve that lies below the x-axis, because that's the anthill going into the ground. So, what do you need to get to sketch a curve? You need at least the intercept and the turning point. So to get the intercept, you can consider when x is 0, what is y? Clearly y is 12, so this will give us the point 0, 12. And when y is 0, we have that 12 minus 3x squared is equal to 0. Now this is a quadratic, which when you solve, you have that x squared is equal to 4. And so x will be x will be plus or minus 2. Now, if x is plus or minus 2, this tells us that the points we have are 2, 0, and negative 2, negative 2, 0. So those will be the x-intercepts. Now, this is it for its intercepts. Now we get the turning point. So get the turning point, that means the value of our derivative has to be 0. So we first get our derivative, and you see that when you differentiate, this is negative 6x. And so when it's negative 6x 0, this is 0 when x is 0. And when x is 0, we have that y is 12. So we have a turning point at 0, 12. Now, is this a maximum or a minimum? Now, you can already tell, since this is a quadratic function, the coefficient of x squared is negative, so this is going to be a maximum. But if you can't tell, you can go ahead and calculate the second derivative. You can say that the second derivative is negative 6, which is less than 0, and therefore will give us a maximum. Now, this is uh this is enough information really for us to get the curve. So let's do just that. So we have a maximum at 0, 12, should be somewhere there. And then we know that at negative 2, 0 and positive 2, 0, we have those turning points. We have those intercepts. So it's our x-axis, uh, and this is the y-axis. That's the origin indicated there. And so the curve will look something like this. Yeah, and this is the cross section of the anthill. So there you have sketched it properly. Now, for the last part, which asks us to determine whether the depression will be completely filled, we need to get the volume of this anthill. Now, how do we get the volume of this anthill? We have to be careful. This curve right here is y is equal to 12 minus 3x squared. To get the volume of this anthill, we would need to, let's think about this carefully. We know that using integration, we can get the volume of solid of revolution. But if we rotate this around the x-axis, what kind of shape are we going to get? If we rotate this curve around the x-axis, we're not going to get the volume of the anthill that's required. The anthill looks something like this. Yeah. And it probably has a circular base. It's more of like a cone, yeah. And so how are we going to get the volume of this anthill? To get the volume of this anthill, we are going to rotate this area here, which I'm shading. We're going to rotate this area here, which I'm shading, around the y-axis. And when we do that, we'll actually have got the volume of the anthill. When we rotate the shaded area about the y-axis, we'll have got the volume of the anthill. I hope you can imagine that. And so, because when we're rotating about the x-axis, our formula for the volume is that the volume is pi times the integral of y squared dx. But now that we're rotating about the y-axis, we have to be integrating with respect to y. And so, in fact, our volume is going to be the integral of pi, you can have the pi outside, x squared dy. Different because we're now going to be looking at horizontal strips. And the limits of our integral, of course, will depend on the bounds of the curve as we see it. And you can see that the area that we're going to be rotating about the y-axis is from the value y is equal to 0 to y is equal to 12. So those are going to be our limits. And then our x squared we can easily get from the equation of the curve, because since y is equal to 12 minus 3x squared, we can easily get x squared. You can see that 3x squared is going to be 12 minus y, and so x squared is going to be 12 over 3, which is 4, minus y over 3. So that's our x squared. And we're integrating from 0 to 12. The volume of
The
the
volume of the
the volume of the anthill will be pi times the integral from 0 to 12, or the function 4 minus y over 3. We're integrating with respect to y. So then we integrate this. What do we get? We'll have pi times uh, 4y minus y squared divided by 6, or computing this from 0 to 12. Now, we substitute the limits in. We'll have pi times 4 times 12 minus 12 squared over 6. You can see that when you substitute the 0 in, then if you substitute the 0 in, then we won't get anything. So there's no need for us to do that. And this is 48 minus 24, which is 24 pi. Now, when you work out 24 pi, it's actually less than 200. And why are we looking at its comparison with 200? It's because we're being told that the depression that has to be filled with the soil from the anthill uh, has a volume of 200, needs 200 meters cubed of soil. And so it has to determine whether this depression will be completely filled. The answer is no. So we can conclude that therefore the depression will not be completely filled. 24 pi is actually much less than 200, so it will not be completely filled. Yeah. So this is item one. Are there any questions on item one, on any particular part of the question? You can have them before we proceed to the next item. Yes, yes, Sharon.
Good morning, sir. I
Good
kind
morning.
of joined late. I'm confused on the first part A, about the area. Okay, about that rectangular land that we're talking about. I'm confused of how we got the solution.
Okay, so had you seen the entire question?
Yes,
Yeah, so the question tells us that the area of the land is 39,200 square meters. So already we know that if the length is x and the width is y, then the product of xy has to be 39,200, because the area is 39,200. And the formula for area of a rectangle is length times width. Now, we let L to be the length of wire that's required to fence this land, lowercase l. And we know that since one side has a wall, we're not going to need to fence that side. And the side opposite the wall will have a gap of 12 meters for the gate. Now, if that side is y, that means to fence side y, we shall need only y minus 12 meters. And then we need 2x for the other remaining sides. Since they are it's a rectangle, those two sides must be equal. So one is x, the other should be x as well. So L should be 2x plus y minus 12. Is that part clear?
Yes, teacher.
Yeah, so if you've done differentiation, then you know that it's not straightforward for us to differentiate when we have these two variables. So we need the expression for L to be in one variable. And so using this equation conveniently helps us to transform the equation 2x plus y minus 12 into the equation for L, into an expression in one variable, just x. You can actually transform it to a variable. You could also decide to write x in terms of y and get the corresponding value for y that would give you a minimum. It doesn't matter. You'll still get the same answer. You'll still get y as 280 and x as 140. So what you do is you after having got the expression for L strictly in terms of x, you differentiate L with respect to x. And when we do that, we get 2 minus 39,200 out of x squared. I said that if you have an expression like 39,200 out of x, the same as 39,200 times x to the power negative 1. That's how you should look at it. And then you use the whole power becomes a multiplier, reduce the power by 1 rule to get you the actual derivative of 39,200 out of it. So that's what we're doing here. And then, for turning points, so and max, for minima and maxima, you have to equate the derivative to zero because it's at such points that the derivative is zero, that a tangent is parallel to the x-axis, and so its gradient will be zero. So the derivative is zero, and then we find the x value that will make the derivative zero. And we see that we have two, 140 and negative 140, but we can't consider x being negative because we're talking about an actual length. Sharon, are we together? Sharon, the person who had asked the question. Anyway, so that's what's going on. Yeah.
Yes, thank you so much, sir. Thank you
Yeah.
so much, sir. I've understood.
Okay, great. Any other questions on this, or we can proceed to the next item? Yeah, so turning points for the first part, direct integration for the next part, and then curve sketching for the third, and then the volumes of solid the revolution for the fourth. Yeah, so that was item one. Okay. So the next item is a bit simpler. It's much shorter actually. An environmental scientist is studying the rate of absorption of a new organic fertilizer in the soil. The rate of absorption R of T in grams per day is given by the function R of T is equal to 60 squared minus 40 plus 5, where T is the time in days. Determine the total amount of fertilizer absorbed by the soil after a certain period. The scientists need to find the integral of this rate function. And so that's the first thing we have to do, part A, find the indefinite integral. And like I said, this is much simpler than the previous question because most of this is really direct and focused. So to find this, we simply integrate each term with respect to t, and we do this by increasing the power of t by 1 and dividing by the new power. This is going to be 6t cubed divided by 3, which is 2t cubed. 40 squared divided by 2, which is 2t squared. And then 5t to the power 1 divide by divide by 1, which is 5t. But we have to add an arbitrary constant of integration because, like you can see, c could be any number. If you differentiate it, when you differentiate a constant, you get 0. And so we have to account for that possibility. Now explain what the constant of integration means in this context. Now remember this R of t is a rate in grams per day, and so we could say that m is actually this 2t cubed minus 2t squared plus 5t plus c, where m is the mass. Now m is the actual mass, uh, the mass of fertilizer in the soil. R is the rate of absorption, and when we integrate R, we get the actual mass of of fertilizer in the soil. Just like how you have velocity, which is a rate, and then when you integrate that, you get the entire distance moved or the entire displacement. Similarly, here we have a rate of the accumulation of the mass, and so when you integrate, you get the entire mass that has been absorbed. And so what happens when when uh what happens when t is zero? Yeah, when t is zero, when t is zero, you just have that m of zero is equal to c. So when they ask you what c represents, c represents the initial mass of fertilizer. C represents the initial mass of fertilizer in the soil. Yeah, so that's for part B. You can see m of zero is c. So c is uh the mass when the time is zero. In other words, the initial fertilizer in the soil. Now part C wants us to find C basically because they've told us that if it is known that 10 grams were absorbed by day one, find the particular solution for your total absorption. So what they're basically telling us is that when T is 1, M is 10. And so we substitute in the expression. We have the expression for M, so this is going to be 2 times 1 cubed minus 2 times 2 squared plus 5 times, sorry, it's times 1, not times 2, is 10 minus 10, 2 times 1 squared plus 5 times 1 plus c is equal to 10. So you have 2 minus 2, which is 0, and then 5 plus c. So you have that 5 plus c is equal to 10. This tells us that c is equal to 5. And so therefore, m is equal to 2t cubed minus 2t squared plus 5t plus 5. And this would be the expression, the particular solution for the total absorption. Yes, Ado.
I was inquiring, like, for a pardon on the part where we consider C to represent the initial mass. So, question is that I was questioning for a pardon on what we based on to say that C represents the initial mass of the fertilizer.
Please ask again.
I was requesting for a pardon on the part where we say that C represents the initial mass. I wanted to ask, what did we base on to say that C represents the initial mass of the fertilizer in the soil?
We okay, so it's initial mass because it's the mass when t is 0. So remember t is the time, yeah?
Yes.
The question says that t is the time in days, studying the rate of absorption of a new organic fertilizer in the soil. Now, of course, this study has to start at a certain point. And when it
Yes.
starts, there might already be some fertilizer in the soil. Now they have to account for it. They can't just say we're just going to start anyhow and just measure the fertilizer. So now when t is 0 at the very beginning, you can see that when t is 0 and you substitute t is 0 in this expression here, what you get is C, which is telling you the mass of fertilizer in the soil when t is 0 is is C, which means that when you're starting at the starting point, the initial mass, in other words, for fertilizer in the soil is C.
Okay, understood. Thank you, sir.
Okay. Any other questions there? Okay, I think this was relatively simple, so we can move to the next item. Okay, a virologist at Uganda Virus Research Institute is studying the transmission pattern of a new virus strain detected in the country. In a controlled observation, a single infected individual transmits the virus to three new people in the first transmission cycle. Each of these newly infected individuals then transmits the virus to three more people in the next cycle, and this pattern continues consistently. The public health team needs to project the total number of infected people after 6 complete transmission cycles to prepare adequate medical facilities, isolation centers, etc. The scenario perfectly illustrates a geometric progression where each term is obtained by multiplying the previous one by a constant ratio. Understanding this exponential growth pattern is crucial for implementing timely interventions to prevent a potential epidemic. Part A, identify the first term and common ratio of this geometric progression. Now, I want to say that this question could be interpreted differently. I mean, in two different ways, and I believe that both of them are correct. So I believe that you could say that the first term, if we say let n u n be the nth term, and so you could decide to let your un be the term at the beginning of that cycle. In other words, the number of infected individuals at the beginning of the cycle, or the number of infected individuals at the end of the cycle. Now, if you use the number of infected individuals at the beginning of the cycle, then your first term, U1, will be equal to 1. Because at the beginning of the first cycle, you have one person. Now, like I said, you could say that if you're considering the cycle again, if you're considering your first term to be the number of infected individuals at the end of the cycle, then your U1 is going to be 3. Because really what the cycle is a movement from from 1 to 3. Okay. U1 to U2. This is the okay, if we use the first one, we're looking at this as the first cycle. But if we're looking at the second one, we're looking at this as the first cycle. So this is a major difference between the two. But the common ratio in both is 3. And so those two answers I believe would be correct for the first part. As long as your part B and C would remain consistent. There's a part C as well. So for part B, we've been asked to calculate the number of newly infected people in the 5th transmission cycle. Now they want the number of newly infected in the 5th transmission cycle. In other words, they want the number of people who become infected in the 5th transmission cycle. Now, if you're looking at this side, the left-hand side, from U1 to U2, that's one cycle. To U3, that's another cycle. To U4, that's the 3rd cycle. To U5, that's the 5th cycle. And to U6, that's the 6th. Sorry, that's the 5th. That's the 5th cycle. So what the number they're looking for actually in this side is U6. Okay. Now we know that for a geometric progression, UN is equal to U1 times R to the power n. In other words, the first time times the common ratio to the power n minus 1, sorry. And so U6, which is the number of people infected in the 5th transmission cycle, is going to be 1 times 3 to the power 5. And this is going to be 243. Now, like I said, if you had decided to use the second method, and you're looking at number of newly infected people in the 5th transmission cycle, here you would just say, you just look for U5. Because we know that U1 is the number of people infected at the end of the first cycle. U2 will be the number of people infected at the end of the second cycle. And so U5 will be the number of people infected at the end of the third cycle. So here, again using a formula, if I use UN is equal to U1 times R to the power n minus 1, here I'll be looking for U5, which is 3 times 3 to the power 5 minus 1, which still comes to 243. So again, depending on how you've defined your first term, so this is at beginning of cycle, number of people at beginning of cycle, infected individuals at beginning of cycle. This is number at end of cycle. Now the reason why I prefer the first one is because when it comes to the third part, one have been asked calculate the total number of infected people after 6 transmission cycles. This is total number of infected people after 6 transmission cycles. Of course, here now you're going to be looking for S7, the sum of the first 7 terms. Why? Because after 6 transmission cycles, U7 will give us the number of people at the beginning of the 7th transmission cycle, which is the number of people at the end of 6 transmission cycles. I could show the cycles again, like you see here. From U1 to U6, we had 5 transmission cycles. So from U1 to U7, we'll have 6 transmission cycles. So to get the total number of people infected, you have to get the sum of the first 7 terms. Now, remember the formula for sum of the first 10 terms of an arithmetic progression will be the first term, first term times the common ratio to raise to the power n minus 1 divided by r minus 1. And so for the 7 terms, it's going to be u1 times r to the power 7 minus 1 divided by r minus 1. This is our first term here is 1 in this case, and the common ratio is 3. This will be 3 to the power 7 minus 1 divided by 3 minus 1, which is 2. And I believe when you work that out, you get 1093. Now, if you had used the other method, you'd have to get, again, we know that sum of first 10 terms is u1 times r to the power n minus 1 divided by r minus 1. You have to get the sum of the first 6 terms, which is going to be u1 times r to the power 6 minus 1 divided by r minus 1. It's going to be 3 times 3 to the power 6 minus 1 divided by 2. This is going to give you 1092. But then you'd have to add, the question says including the initial case. And you have to realize that using the second first term, we're using the first term as 3, does not include the initial case. It only counts the number of people at the end of different cycles. So it does not count the first person because the first person is at the end of the zeroth cycle. And so the first person has not been counted. And so if you use the second method, you have to include the first person by adding 1, which will give you 1096 as well. I hope this makes sense. Any questions here? Okay, y is n equal to 7. Question from Louise. n is equal to 7. Again, for the first method I said, it counts the number. If you're using your first term as 1, that means you're counting the number of infected people at the beginning of at the beginning of the cycle. And so if they're asking us total number of infected people after 6 transmission cycles, realize that the first cycle is from 0, 1 to 0, 2. The second cycle is from 0, 2 to 0, 3. The third from 0, 3 to 0, 4. The fourth from 0, 4 to 0, 5. The fifth from 0, 5 to 0, 6. And the sixth from 0, 6 to 0, 7 to U7. Sorry. U1 to U2, U2 to U3, to U4 to U5 to U6 to U7. That's what makes the cycle. That's what makes the cycle 6. Why didn't I subtract the 1 from the formula in part B? In part B, the question wasn't asking for a total number. It was asking for new infections within the cycle. You look at the number of newly infected people in the 5th transmission cycle. So it's not asking for the total number, it's asking for just new infections that come within that cycle. So it's asking for a number of terms there. Josh, I don't know if that answers you. It's asking for a particular position in the geometric progression. So in the second method, we're looking at the 5th term. The first method, we're looking at the 6th term. It just depends on how you define it. I think if you decide to just list the progression, yeah. If we list the progression, you can list it. You can see that. So we have 1, 3, 9. These are powers of 3. 27, 81, 243, 729, and so on, right? What does this mean? It means in the first cycle, one person infects 3 people. The second cycle, these 3 people infect 3 other people. So 9 people are newly infected. In other words, these 3 people infect 9 people. The third cycle, 9 people infect 27 people. The fourth cycle, 27 infect 81. The fifth, 81 infect 243. And the sixth, these 243 infect 720, 729. Now you can add all these up, you'll actually get the 1000, what? The 1093. But now if you're looking at the second geometric progression, what does it start with? It starts with 3. 3, 9, 27, 81, 243, 729, and so forth. What is it saying? In the first cycle, 3 people are newly infected. The second cycle, 9 people are newly infected. The third cycle, 27 people are newly infected. The fourth cycle, 81 people are newly infected. The fifth, 243 are newly infected. I hope we can see the difference between the two and how they are both correct, as long as you know what you're considering. Yeah. So actually, if you wanted to calculate the sum, you could actually have listed down these and just added them manually as well if you wanted. So, Adolf, you had a question. I don't know if it has been answered. Seems like you wanted to ask something.
Yeah, it has been answered.
Okay, that's great.
Oh,
Okay. Can you hear me? the recording to this seminar is going to be uploaded to the YouTube channel. So you can go back and watch. Yeah, so we are proceeding to item 4. Item 4, that now it is paper to work. From item 4. In a warehouse in Kampala's industrial park, a worker needs to lift a heavy crate of mass 80 kgs using a rope thrown over his body. A worker who has a mass of 90 kilograms pulls downwards on the other end of the rope. The system is modeled as two particles connected by a light, inextensible rope over a smooth pulley. The warehouse manager needs to calculate the acceleration of the crate and the tension in the rope to ensure the rope's breaking strain is not exceeded and that the crate can be lifted safely without the worker losing control. This analysis is crucial for safety and for selecting the appropriate equipment for the job. The task that we have to sketch a system and label the forces acting on the crate on the worker. Then we have to apply the termed second law to both the crate and the worker to form this homogeneous equation. And we're going to solve the equation to find the acceleration of the system and the tension in the rope. So we shall start by sketching. So we shall sketch. What do we have to sketch? We have to sketch the crate, the pulley, or the wheel, and then the worker and the spin. For those who do physics, I think it's important to note that we are using a light inextensible string, so that strain energy is not kept in the string. In other words, the string should not be elastic. That's what will help us develop the tension in the string. Otherwise, each and every, if at all the string was elastic, you may find that all the force that you'd have applied in lifting the crate is being stored in the string and it's not being used to lift the crate. So our sketch is going to look something like this. We have a wheel or a pulley, and then we have crate. I'm using the box to easily model it. So the crate weighs 80 kilograms, and if we are to use weight, it's going to be 80 times g. So we can just say 80 g. So we have 80 g. Then whatever is going to lift this crate is the mass of the worker, and the worker weighs 90 kilograms. So we shall model something like that, and for that we shall use 90 g. So in the in the in the in the string we have tension. I think let me make it a bit bigger so that you can easily see what's happening. So this is the pulley. So it is 90 g, and then this is 80 g. So we have tension in the string. See? See. And since it's the same string, the tension is all the same. There's tension here, there's tension there. So now what the predicted motion would be this crate going up. a particular acceleration, and since it's behaving as one entire system, then the same acceleration for the worker going down. So this is what our sketch will look like. So in the sketch, you have to show the forces in the string, the forces acting on the crate and the worker, and also the acceleration. So that is our sketch. So now part B, this is asking us to apply Newton's second law of motion. Newton's second law of motion is F is equal to ma. And we're going to apply this so that we can form two simultaneous equations. F is the resultant force acting on a particular body. So we are going to consider the two bodies. Let's first use the crate. So we see that the crate is moving up. And what that would mean is, let me just draw something here. We have ATG, we have T, the crate moving up like that. What that means is that the tension is greater than the force or the weight of the crate. So that implies that we can say resolving vertically, T minus AT G is equals to MA, where M is the mass of the crate. So T minus 80 into 9.81 is equal to 80 A. So T minus 784.8 is equal to 80 A. And this is our equation 1. Yes, Leonard,
Yes,
your hand is up.
good morning, sir.
Morning to you.
Actually, what I wanted to ask from you is like the value of G. Some teachers have been telling us, like, for the case of math, that it has to just be 9.8.
Yeah, you could use 9.8. Okay, they could
Sorry?
specify for it to be 9.8, but the standard value is 9.81.
And
You
some
get,
other teachers have been telling us, like, for the case of math, that in case, even though
you have gone off. I can't hear you. Yeah, so okay, I understand the point you're getting across. So what we shall do, let's use 9.8.
for math,
But
then 9.81, that is for physics.
let's use 9.8. Okay. So 80 times 9.8 gives us 784. So 784. This is our equation 1. Then we shall also look at the worker. For the worker, we have the tension, we have 90 G, and we have the acceleration. So resolving vertically, going to give us 90 into 9.8 minus T is equal to 90. So 90 times 9.8 is 882. minus T is equal to 98. So that's our second simultaneous equation. Then, when you go to part C, we are going to solve the equations, then find the acceleration of the system and the tension thereof. So part C, we're going to solve 1 and 2 by adding. And what that means is we're going to do 1 plus 2. What that gives us is T minus 784 plus 882 minus T is equal to 80 plus 90 A. Yeah. So we see that the T's will cancel and we shall remain with 882 minus 784 is equal to 98. And then set aside you have 170. So we shall say 178 is equal to 98. And 8 is equal to 98 divided by 170. And A is equal to 0.576 meters per square second. So that is the acceleration. Then the tension shall use T minus 784 is equal to 80 A. So the tension is going to be equal to 80 times 0.576 plus 784. So the tension is equal to 830.08 newton. That's the tension in the string. So that is question 4 or item 4. Are there any questions? If there are no questions, let's go to item 5. Item 5 is relatively easy and short. Item 5 says a team of engineers is designing a new cable stayed footbridge over a stream in Kampala Park. A key cable is attached to the central pylon and exerts a force of 1,000 newtons per ton against the horizontal. To ensure the bridge's stability, the engineers must calculate the horizontal and vertical components of the force. The horizontal component will affect the lateral stability of the pylon, while the vertical component affects the weight of the bridge deck. Accurate calculations of these components is crucial for selecting appropriately strong materials for the pylon and the deck supports, ensuring the safety of hundreds of daily pedestrians. Calculate the horizontal component of the force in the cable, the vertical component of the force in the cable, and if the angle were increased to 45 degrees, what would happen to the magnitude of the horizontal component? Explaining your reasoning. So, what do we see here? I'll use a sketch. I don't know whether you're all familiar with what central pylon bridge, cable stayed footbridge, and all that. But we shall use, I'll try to sketch it. So, sketch is going to be something like this. So, you have a bridge, a footbridge, yeah, and you have a pylon that is supporting this footbridge, such that we have the bridge deck being supported by cable, which is attached to the pylon. So you have a pylon, something like that, and then we have our cable attached to the pylon at that angle. So what do we know? Well, we know that the vertical component supports the bridge deck. Where is the deck? And then the horizontal component affect will affect the lateral stability of the pylon. And this is our pylon. So if we are to use a simplified model, we can have a point whereby it is we have a force T implying that we agree. But we know that the force in the cable T is equal, the force T in the cable is 1000 newtons. So to find the horizontal component, let me call it FH. FH would be equal to 1000 cos 30 degrees. And FH will be equal to 866.0254 newtons. And now the vertical component, FV will be equal to 1000 times 30 degrees, and that's equal to 500 newtons. So the next question, that part C, is asking us to check or to find out the magnitude of the horizontal component if the angle is increased to 45 degrees. So if the theta is increased to 45 degrees, it's the angle, where theta is the angle of inclination of the cable. So if theta is now 45 degrees, we have to find the horizontal component. So now FH would now become 1000 cos 45. And I think it's important to sketch it here again. And then we have 45 degrees there. So the horizontal component will be 1000 cos 45. And FH is therefore 707.1068 newtons. So what do we observe? We observe that the horizontal component reduces. It reduces. So, and we can show that, let me call it FH2, and this FH1. So let's get the ratio FH1 to FH2 is equal to 866.0254 divided by 707.1068. And that's going to be equal to around 1.25. So we see that FH2 is now equal to 1 over 1.225 FH1, which gives us 0.8163 FH1. So FH2 reduces FH1. FH2 becomes the new horizontal component, but it's reduced because the angle has been increased. So by increasing the angle, we notice that the string is becoming more and more vertical. So all the force in the string is being turned into the vertical component. So that is what is happening to the magnitude of the horizontal component. So our reasoning could be that horizontal component depends on theta by cos theta. And we notice that as theta approaches 90 degrees, cos theta approaches 0. So that means that the horizontal component FH also approaches 0. Thus reduces. So yeah, that's what we observed from item 5, maybe part A, B, and C. Are there any questions? Okay, looks like there are no questions. Let's move to, yes, Esther. Unmute and ask. Esther, please ask the question. I don't know if you mean to ask the one I see in the chat. So in what we are saying is, I think we just have to know what these parts, what we're talking about. So we're talking about a bridge being supported. That's the central pylon. Yes, the touch central pylon which exerts 100 force of 100, so 1000 newtons, so under 30 kg. To the horizontal component will affect the stability, the lateral stability. That means the bridge shaking or moving sideways. That's the horizontal component managing that. While the vertical component supports the weight of the bridge deck. So you have, or we could look at it like this. So let's say we have a bridge, yeah, and then we have, let's say, pylons like this, and then we have cables, yeah, and these cables are supporting the bridge. So we could have this as our 30 degrees, whereby this 30 degrees is also the same here. Or we could have 30 degrees here, and also that's the same 30 degrees right here. So at this point, let me call it B. At point B, we have that 1000 newtons in the cable and then 30 degrees of the bridge deck. The inclination of the cable to the bridge deck. That's how I came up with that sketch. Yeah, I think we can proceed to item 6. Item 6, we have Uganda Life Authority is designing a new system to safely tranquilize aggressive elephants from a distance. Tranquilizer that is fired from a high pressure gun at an initial speed 80 meters per second. To ensure the dart reaches an elephant typically 150 meters away, the ranger needs to know the correct launch angle, ignoring air resistance. The ranger must calculate the required angle so that the dart's horizontal range is exactly 150 meters. So this ensures the humane and effective immobilization of animals for recollection or medical treatment. So we are supposed to set the formula for horizontal range R of a projectile launched with a speed u and angle theta. We could, the formula is R is equal to u squared over g times sine 2 theta. So yeah, but you could go to the whole, you could try or attempt deriving it. Yeah, so that you know where it comes from. But that is formula, simple as that. So we are then tasked to calculate the two possible launch angles that will give a range of 150 meters with an initial speed of 80. So, given that R is 150 meters, while theta is unknown, and then u is 80 meters per second, uh, shall substitute into the formula and shall have 80 squared divided by 9.8 sine 2 theta is equals to 150. So sine 2 theta is equal to 150 divided by 80 squared times 9.8 pounds. And that's equal to that is equal to 0.230. Is there another formula for it? I do not think so. Maybe if you have derived it. Yeah. So from this, we shall find the acute angle. The acute angle corresponding to 0.2. So that will be the arc sine or sine inverse of 0.230. And that is equal to 13.30 degrees. So remember, for projectiles, yeah, for projectiles, theta ranges from 0 to 90 degrees.
So we're not hearing you. Requesting you be audible.
I'm saying, sorry, 9.8, but still the same value. That's a mistake. So change that. So this is 9.6. Yeah, thank you for that. Yes, I was saying for projectiles, theta ranges from 0 to 90 degrees. So what that means is that if you have 2 theta, then 2 theta is from 0 degrees to 180 degrees. So we have to find the two angles corresponding to this acute angle of 13.3. But if you have to look at the quadrants we have that sign is positive in the first and the second. So we are going to find the two angles in the one in the first quadrant and one in the second. So this implies that 2 theta is equal to 13.30 because that is positive in the first quadrant. And in the second quadrant, we are going to find the other angle, which is going to be given by 180 minus 13.30. And that is equal to 166.70 degrees. So that implies that theta is equal to 13.3 divided by 2, which is 6.65 degrees. Then 166.7 divided by 2, which is equal to 83.35 degrees. So those are the two possible launch angles. That's part B. Then part C says which of the two angles would be more practical for this application and why. So by that, we have to consider the context of the question. We have an elephant that we have to treat, or we have to, yeah, we have an elephant at which we are shooting a tranquilizer dart. So now that means that you want this to be as quick as possible. You want to immobilize the elephant as quick as possible. So we notice that with the words I'm using, there are aspects of time. So we need it to be faster. We need this to have a faster effect. But we have two possible launch angles. That means we have to know which of the two is best. Now, to know which of the two is best, we are going to use the aspect of time of flight. Yeah, and we are going to use that because we have, let's say we have an elephant here, point B, and then we are shooting from point A. So we have two possible angles, and all we know is the general shape of a projectile is going to be something like that. This can be theta, and this is u. So the elephant is at point B, and the gun is at point A. So we're going to shoot from A to B. When we shoot from A to B, the tranquilizer gun or the tranquilizer itself is going to move through a certain distance, as we have seen, 150 meters. That is the range. And then we want to know how long it will take from A to B. But there are two possible angles. So we shall check the time of flight using both. The time of flight, let's say for theta is equal to 6.65 degrees. Time of flight t is equal to 2u sine theta over g. So t is equal to 2 times 80 sine of 6.65 degrees divided by 9.8. That gives us t as 1.889 seconds. So we check for the other one. So theta is equal to 83.35 degrees. Time of flight is going to be equal to 2 times 80 sine of 83.35 degrees divided by 9.8. And therefore t is equal to 16.2267 seconds. So we see that if we use angle B or if we use 83.35, we'll have a longer time. That means the more practical launch angle theta is 6.65 degrees. And that's item 6. Are there any questions? Okay, it appears that there are no other questions. Let's go to item 7. So item 7 about relative motion. We have two boats, A and B, on the Calbert. Boat A is located 2 kilometers due east of lighthouse and is moving due north at 20 kilometers per hour. Boat B is located 3 kilometers due north of the same lighthouse and moving due east at 15 kilometers per hour. The Coast Guard needs to determine if the boats are on a collision course, and if not, find the distance of closest approach between them for certain use. This problem involves analyzing the relative motion of one boat respect to another. Find the initial position vector of boat B relative to A. Find the velocity vector of boat B relative to A. And we're supposed to calculate the shortest distance between the two boats during their motion. So we are going to start by sketching, and we have our lighthouse. Let's call this the lighthouse. The lighthouse is here, and from boat A is located 2 kilometers due east of the lighthouse. So A is here, and this is 2 kilometers. While B, and boat A is moving due north at 20 kilometers per hour. Now boat B is located 3 kilometers due north of the same lighthouse. So boat B is here. This is 3 kilometers, and it's moving east at 15 kilometers per hour. So we are supposed to find the closest distance to approach, the position vectors, and the velocity vectors respect to each other. So at A, let's find the position vector. So position vector, we're going to find the position vector of A. Position vector of A, if let's say our lighthouse is at 0, 0, A is at 2, 0 kilometers, and B is at 0, 3 kilometers. So we are going to find the position vector of B relative to A. So we are, in other words, finding position vector of B if we're using A as our reference. So that means we are going to have position vector of B minus the position vector of A, which is equal to 2, 0 minus 0, 3. And that gives us, sorry, the other way around, the other way around. So mistake. So we shall have 0, 3 minus 2, 0. That's equal to negative 2, 3 kilometers. That's the position vector of B relative to A. The next thing we're going to do is find the velocity vector of B relative to A. The velocity vector of B relative to A is also going to be equal to the velocity of B minus the velocity of A. So let's first find the velocity of B and the velocity of A. So velocity of B is equal to 15, positive 15 and 0. This is kilometers per hour. And the velocity of A is equal to x is 0, y is 20 kilometers per hour. And these are positive because A is moving upwards and B is moving to the right. And also we have zeros wherever we have zeros because it is either perfectly horizontal, that means it only has x components, or it's perfectly vertical, that means it only has y components. So the velocity vector of B relative to A is going to be equal to 15, 0 minus 0, 20. So we have 15 and negative 20 kilometers per hour. So that's the velocity vector. So we're going to calculate now the shortest distance between the two boats. Now for shortest distance, we are going to use the relative yes, we're going to find the difference in the vectors of these uh, okay, the vectors that describe the positions of these boats with respect to time. Yeah. So let me say let's let's first consider boat A. Now boat A, its position, we can call this actually node. I don't know, so I differentiate it from what I'm explaining here. So for boat A, its position vector A is equal to its initial position vector plus the velocity vector of A times time. So RA is equal to 2, 0 plus 0, 20. That is RA. That's going to be equal to 2, 2 plus 0, which is just 2, just 2. And then here we shall have 20 feet. That's kilometers. Now for boat B, R B is equal to the initial position vector of B plus the velocity of B times time. So what that means is that the position vector of B at any time is equal to 0, 3 plus, let me check if that's right. Yeah, 0, 3 plus 15, 15, 0 times T. And that's equal to 15T or 15T3 kilometers. So to find the shortest distance is the distance between these two boats at any time T. So at any time T, the distance between them, the distance D is, so D is equal to the difference in the position vectors of these two boats, which is equal to 15T3 minus 220T. And that's equal to 15T minus 2 and then 3 minus 90. Next thing we're going to do is find the value of t that will help us find the distance d between the two boats. So for sure, we know that the magnitude of d, the magnitude of d, let me just keep is equal to d, will be equal to 15t minus 2 squared plus 3 minus 20 t squared. This is all under square root. So d will be equal to, let's square both sides. So we have d squared will be equal to 425t minus 60t plus 4 plus 9 minus 120t plus 400t squared. So d squared will be equal to 625 t squared minus 180t plus 13. The condition here is that if collision is to occur, then or if we have to have the shortest distance between them, then the derivative of this function, of this expression, has to be equal to 0. So we're going to find the derivative of this expression with respect to time. So d dt of d squared is equal to d dt of 625 t squared minus 180t plus 13. So, this has to be equal to 0. So this will mean that, let's do a differentiation here. If we do the differentiation, we shall have 625 times 2. So 625 times 2, that's 1250 minus 180 is equal to 0. 2 will be equal to 180 divided by 1250, and that's equal to 180. 180 by 150 gives us 0.144 hours. So that's the time it will take if collision is to occur. So we shall substitute this time into the vector d, and we shall find, or we shall substitute into the magnitude of d and find out where it actually collides. So substituting is equal to 0.14 gives us d is equal to 15 times 0.144 minus 2 squared plus 3 minus 20 times 0.144 squared, all under square root. So the shortest distance d is going to be equal to 0.2 meters, and that's 200 meters. So the shortest distance between the two boats during their motion is going to be 200 meters. So that is how we would do item 7. Are there any questions?
Yeah, so can we use the other method of just calculating, let us say, relative velocity, then you multiply it with the difference between the two distances? Can it give the same answer?
I beg your pardon?
Like the method you've used, isn't there another method of calculating closest distance, like the distance of approach, the one of having the difference between the two distances multiplied by the relative velocity and the time, then you equate them to 0? Can it give you the same answer?
I didn't check that out, but I think you should try it out and let us know.
Okay,
Um,
okay,
yeah,
let me see.
for the sake of time,
Okay, thank you.
yeah, you're welcome. Hello. um, Mr. Johan is up. I don't know if you had a question. Sorry, you're you're breaking. It's a bit unclear. Maybe you can type it in the chat. Maybe you can type the question in the chat. Will be attended to. No, but in the meantime, let's proceed to the next item. So, item 8 is a simple question in discrete random variables. The mobile network operator is analyzing the number of daily customer service calls received at its Kampala call center. The random variable is supposed to be x, not y, represents the number of calls related to mobile money transaction issue. Based on past data, the probability distribution of y is partially known. The company wants to fully define this distribution to staff the call center appropriately, ensuring short wait times and high customer satisfaction. So, the question about how do you know if the two have collided is you look at their displacement, yeah? If you look at the equations of their displacement, the expression of their displacement is, yeah, you have R of A and R of B, and you equate them. The time should be consistent the time should be consistent if they ever collide, if you solve that equation, we should get the same T. But here we can't get the same T because you have that 2 is 15T and 3 is 20T. And so you'll have T as 3 over 20 for the first, and then 2 over 15, 3 over 20 and 2 over 15, which are not equal. So that shows you that they will never collide. Uh, Going back to item 8, find the value of A. If you look at those probabilities, um, if you look at those probabilities, yes, true or false, the answer is yes. If you look at those probabilities, their sum has to be 1. So we won't be looking at values of x from 0 up to 4. the sum of those probabilities should be 1. And so 0.1 plus 0.3 plus A plus 0.2 plus 0.1 should be equal to 1. And so you realize that this is the same as 0.7 plus A being equal to 1. And so A should be equal to 0.3. Now, part B was asking the expected number of daily mobile money related calls. For the expected value of X, this is the same as sum of all X values and the product of all X values and their product probability, sum of all of them. So this will be 0 times 0.1 plus 1 times 0.3 plus 2 times A, which was seen is 0.3, plus 3 times 0.2, plus 4 times 0.1. Now when you add these up, you have a 0.3 plus 0.6 plus 0.6 plus 0.4 gives us 1.9. So this is the expected. This is the expected number of daily mobile calls. Now, if you look at part C, it asks for the variance. We just use a formula for variance, which is the expectation of X squared minus the mean squared. Now, the expectation of X squared will just be the sum and the product of X squared and the probability. So you have 0 squared times 0.1 plus 1 squared times 0.3 plus 2 squared times 0.3 plus 3 squared times 0.2 and then plus 4 squared times 0.1. And then we're subtracting the mean square, which is 1.9. The fun is 1.9 squared, so don't forget to include that. We're subtracting 1.9 squared. Yeah, so you have 0.3 plus 4 times 0.3, which is 1.2, 9 times 0.2, which is 1.8, and then 16 times 0.1, which is 1.6. And you're subtracting this, which is 3.61. Eventually, you end up with 4.9 minus 3.61. Yeah, which should give you 1.29. Yeah, this was pretty straightforward. Any questions here? Okay, I don't think so. Item 9. Item 9 is a simple question on the trapezium rule. We've been asked first to find the exact value of the integral. So this integral over x squared with respect to x, increase the power by 1 and divide by the new power, complete from 0 to 6. So this will be 6 cubed over 3 minus 0, 0 cubed over 3 0, will be 72. So 72 is the exact value of that integral. Now been asked to estimate the trapezium rule using 3 strips. Okay, so 3 strips. If you look at the curve Let's look at the curve. But just if we can just sketch it, look something like this. X, so that's 0, 2, 4, and 3. Just fix this. You want us to find the area under it, under this curve. What do we do? In trapezium, we'll have these strips. So look at the strips, the different strips. And then we estimate these to be trapezium. Until you end up joining that point to that point, this point to this point, and this point to this point, and then find the respective areas. That's basically what you're doing when you're substituting in the formula, because in the formula you have x and the value of f of x, and you do it for each of these points that you're going to consider, depending on the number of strips. So you have 0, f of 0 is 0, and now f of x is x squared. We can actually just put x squared here. X and x squared 0, 4 squared is 16, and 6 squared is 36. So yeah, so the integral from 0 to 6 of x squared with respect to x will be approximately, so we use approximately a half times h. H will be 2 because that's the length of our strip. And then for the extreme ends, the values of x squared at the extreme ends, we have them multiplied by 1. So we'll have a 0 and 2 times the ones in the middle. So 2 times 4 plus 16 and then plus 36. And the reason is really that the ones in the middle appear in 2 trapezia, but the ones at the extreme ends appear in just 1 trapezium each. So that's why we have them like that. You know the formula for area of a trapezium is a half h into a plus b, where a and b are the 2 parallel sides. So in this case, you can see that 2 appears in the first trapezium and the second, 4 appears in the second and the third, but 0 and 6 both each appear in the first and third respectively. If they appear in just one, which is why they're not being multiplied by 2. Put a dot there. So this that we're computing when you work it out is equal to 76. And so that tells you that that would be the area you would have got, or the value of the integral you would have got if you had used the trapezium rule with 3 strips. So part C wants us to get the percentage error. The percentage error is simply the absolute value of the error divided by the exact value. So we always make the comparison with the exact value and then multiply this by 100%. So the absolute error is the absolute value of 76 minus 72. And we're dividing this by 72 and multiplying by 100%. So this is 4 over 72 times 100%. Now 4 over 72 is the same as 1 over 18. And so when you work that out, you can get your answer. 4 decimal places, this will be 5.5556%. You know the exact value is actually 5 and 5 over 9%, which is actually 50 over 9%. Yeah, so 54 for decimal places. Any questions there? I think also trapezium rule is probably one of those questions which you're happy to see. Yeah, so I don't think that was. If there any questions there, we can discuss them, but I think we can proceed to the next. And our last question, actually, which is a question on errors. Yeah, so for item 10, we've been given this item, a team of civil engineers conducting a land survey for a new road project connecting two towns in the Busoga region. We need to calculate the total area of a rectangular plot of land. The length of the plot is measured as 250.5 meters with a possible error, sorry, 0.2 meters. Plus or minus means it could be higher or lower. The width is measured at 180.3 meters with a possible error of plus plus or minus 0.1 meters. The procurement department needs to know the maximum possible error in the calculated area to budget for extra materials that might be needed due to measurement uncertainty. So, part A, we've been asked to calculate the nominal area of the plot. So that's using the measured length and width. So that nominal area is going to be the 250.5 multiplied by the 180.3. That's what part A is asking for. And that's 45,165.15 square meters. So that's for part A, that's not a difficult one. Now for part B, they're asking for the maximum possible absolute error in the area calculation. Now, so what this is asking for is what we're looking for is the maximum possible error. So the maximum value that delta A could take on. Now, if you look at delta L, of course, absolute implies that we're looking at this. If you look at delta L, the new area, which is going to be A plus delta A, will be a product of L plus delta L plus the width plus the error in the width. Sorry. If you multiply these, you should get length times the width plus the width times delta L plus the length, sorry, plus the length times the error in the width plus the product of the errors, delta L and delta W. Now, the LW and the A are exactly the same. And so on the left-hand side, we'll just be left with delta F. We subtract that from both sides. And then this product of errors here is negligible. And so we can consider just the length times the error in the width plus the width times the error in the length. And so this will give us the maximum possible error. Now you could decide to put absolute value times of each of these errors, but if you don't, it's okay. It's totally implied. So we'll have that the maximum of this, so the maximum error is the actual length, the measured length times the maximum error in the width. Maximum error in the width was zero. Sorry, this is W delta L, so 180.3 times 0.2 plus 250.5 times 2.1. That's what you're supposed to get. And when you work this out, you get 61.11 to be square meters. Now, alternatively, if you didn't do this, you could have got a maximum possible area, maximum uh, possible measured area. The maximum possible area, which would have been 250.7 times 180.4 when you add the area terms to each of those. And this will give you 226.28. And then the minimum of the same, would be 250.3 times 180.2. And this will give us 45104.06 square meters. Now, what you do is you take the average of these two, average of those two, so the maximum error will be the average of those two. 45226.28 plus
Wait, teacher,
45104. Yes,
excuse me,
please.
sir. I have a
Yes.
question. For maximum area, is it when you're getting max of the area, both of them will add, not subtract the minimum deviation, the change? Because 180.5,
Uh,
I thought you're supposed to
no,
add plus the 0.1.
the width is 180.3. The measured width is 180.3. I think you're seeing it as a 5, but it's actually point.
Oh,
Yeah.
thank you.
Yeah. So again, if you do this, sorry, you don't get this. Where is, if you get the error for each of these, um, oops, um, hmm. So the error that comes from this, when you compare it with the original area, is going to be 61.13 square meters. If you compare it to the original area, so you subtract the original area from this, and if you compare this with the original, the area you're going to get is 61.09 square meters. So the average you get is the average of these two, and the average of these two will give you 61.11 square meters. That's the alternative. Sorry for that mistake. You get, yeah, you get that's how you'd work that out. So that's for the second part, uh, the maximum possible absolute error in the area calculation. It's a little bit questionable because you realize that we have left out this, so that means that bit also contributes to the error. And also, I think you realize that this is also a higher error than the 61.11. But that's how the calculation is. It's error analysis. Even in that, we have some things that we neglect. Yes, yes, Sharon. Sharon, you had raised your hand. Okay, I guess it was in error.
Good afternoon, teacher.
Yes, please.
I'm kindly, I'm kindly requesting to please remind me why we left out the LW and the change in L and the change in W.
This circled one here.
No? Yeah, here. Where we have the area plus the change in area.
Uh, the one right here, the one I'm pointing an arrow at.
Yes.
Yeah, so we leave it out because it's negligible. So the errors are deemed to be really, really small, ideally. Yeah, ideally the errors should be really, really small. So if you have something that's really, really small times something that's really, really small, you get something that's even smaller. Yeah. So if you have, for example, if you multiply 0.1 times 0.2, which are two small numbers, you get an even smaller number, which is 0.02. So that's why we leave it out. Of course, 0.02 might seem significant here, but if you look at what we're looking at an area of, 45,000, over 45,000 square meters, yeah? 0.02 is negligible. So that's why we leave it out. I hope that answers you. So when it comes to calculating the relative error, this is simply a comparison of the absolute value of the error, which we've got, divided by the exact value, the nominal value in this case. This will be 61.11, 61.11 divided by 45,165.15. Yeah. When you work this out, you should get 0.001135.3. We have, four significant figures. And the percentage error is just the relative error times 100%. The percentage error will be 0.001353 times 100%. And so, yeah, we just shift the decimal. We just shift the decimal a little in front. That will be 0.1353%. Yeah. Any questions there? Okay. So that's our last question, and that would mark the end of it. Yes, Liz.
Could you please help me differentiate between when we are finding relative error, as in relative error alone, the way we point it right now, and then when we are looking at error propagation? Because at school, we are told that, I think, okay, I really confused that too. I think when you're doing error propagation is when we divide by the approximate, then here you divide by the exact. I really get confused between the two.
Okay, so you should actually always divide by the exact. It's just that actually in this case, we don't even know the exact, yeah? Because we are saying these things could have been measured with an error. So what we are doing here is we're dividing by the nominal area. So it really depends on the question it really depends on the question. So don't be flexible in the way you approach the question. Let me write nominal here uh, just just for the sake of this particular question. But if we're looking at questions where questions could be worded differently, the error is usually compared to the exact value because it's a deviation from that particular value. It's like when you're computing percentages of anything. For example, if you're computing percentage profit or loss is a deviation from the cost price. The cost price is your reference point. So you're looking at how much it has changed from that. So in error, we're looking at how much it has changed from a particular value. And if we don't know the value, then we have to use a nominal value, which was the measured value in this case. But if we know the value, then we have to use the exact value because it's a deviation from that. For example, if you look at the question we did just above on the trapezium rule, we knew that it was a deviation from 72 because 72 is the exact value, and that's why we used it as a denominator here. But in this particular question, we don't know what the area is. So what's actually happening is we assume that we were correct, and then we look at the extreme cases, whether when we have got like have the highest possible area and when we have like the lowest possible area. And then we get the average of those two, have the error that we're going to use as our maximum error. divide that by the nominal value, and that will give us a sort of range of the highest percentage error. So we know that our value will lie in a particular range. That's really what's going on.
Oh, thank you.
Yeah, all right. So yeah, uh, there's a playlist on errors on our YouTube channel, so you could also catch more information on there if you still have any more questions. Yeah.